created by MindSticks Foundation Trust.
Welcome, students! Today's explainer is going to guide us logically from basic counting all the way to understanding the powerful formulas behind mathematical growth. We'll find the nth term, reveal the arithmetic progression formula, solve some practical examples, tackle real-world word problems, and finally compare arithmetic with geometric growth. Let's get started!
Section 1. Finding the nth term. Let's look at a very practical challenge that we often face when dealing with sequences of numbers.
Take a look at this sequence: 5, 8, 11, and 14. It's quite easy to spot that our common difference is 3. We are simply adding 3 each time. But what if I asked you to find the 100th term? Simply adding 3 over and over again 99 times is going to be incredibly tedious and frankly very prone to silly errors. We absolutely need a better method.
Section 2. The AP formula revealed. You know, mathematicians really don't like doing tedious work if they can avoid it through logic. So let's see if we can establish a universal rule for this pattern.
By observing the pattern of adding that common difference repeatedly, mathematicians derive this highly elegant shortcut. The formula is T sub n equals A plus n minus 1 multiplied by D. This simple equation is literally the master key to unlocking arithmetic progressions.
Let's carefully unpack what each of these letters actually means, so we know exactly what to substitute when solving our problems. T sub n is the specific final term we want to find. A represents the very first term in our sequence. N is the position number, like the 5th place or the 100th place, and D, well, that's our common difference.
As illustrated here in our source text, instead of adding our common difference D 99 times to get the 100th term, we can simply plug our values directly into this formula. It lets us jump straight to the answer without all those intermediate steps. A real time saver.
Section 3. Solving sequence examples. Now that we have our mathematical tool clearly defined, let's test it out on a standard sequence problem to see how it functions in practice.
Consider this sequence. The first term is 5, the second is 11, the third is 17. The common difference here is clearly 6. Now, here is an interesting question. How do we mathematically prove if the number 301 belongs anywhere in this specific sequence?
We approach this logically by assuming 301 is indeed the nth term. So, we substitute 301 for t sub n, we substitute 5 for our first term a, and 6 for our common difference d directly into our newly learned formula.
Let's work through the algebra step by step. 301 equals 5 plus n minus 1 times 6. We expand the bracket to get 6n minus 6. Simplifying this gives us 301 equals 6n minus 1. Adding 1 to both sides leaves us with 302 equals 6n. Now, notice what happens as we solve for n. We end up with n equaling 302 divided by 6. This division gives us a fraction, specifically 151 divided by 3, which is definitely not a whole integer. This brings us to a crucial conceptual point. Because n represents a physical position in a sequence, like the 1st, 2nd, or 50th spot, it absolutely must be a whole natural number. You can't have a fractional position in a sequence. You can't be the 50.3rd person in a line, right? Therefore, because our result is a fraction, we can definitively conclude that 301 is not in this arithmetic progression.
Section 4. Real-world word problems. Mathematics isn't just about abstract numbers on a page. This formula applies beautifully to real-world scenarios as well.
Let's observe the case of a young boy named Kabir. His mother diligently noted his height on each birthday. At age 1, he was 70 centimeters tall. At age 2, he was 80 centimeters. And by age 3, he was 90 centimeters tall.
His observant aunt, Mira, correctly noticed that his height is growing in a predictable arithmetic progression. This gives us a first term, our A, of 70, and a common difference, our D, of 10 centimeters per year. She tasked us with finding out his projected height at age 15, assuming this constant growth continues. So our target position N is 15.
By thoughtfully substituting these values into our formula, we calculate T sub 15. That is 70 plus 15 minus 1, which is 14, multiplied by 10. 14 times 10 is 140. Add that to our starting height of 70, and we calculate that Kabir will be an impressive 210 centimeters tall when he's 15 years old. That is quite a tall young man.
Section 5. Arithmetic versus geometric growth.
To conclude our explainer today, let's explore a classic historical story. This tale brilliantly illustrates that adding a constant difference is not the only way things can grow over time.
Once upon a time, a king hired two expert horse-riding teachers, Tara and Mira, to instruct his children for 1 year. When asked about their required salaries, the two teachers requested two very different payment structures.
Tara's request was quite straightforward. Give me 100 gold coins the first month and increase the amount by 100 gold coins every single month. This is a classic arithmetic progression. Mira, however, asked for this. Give me just 10 gold coins in the first month, and every month simply double the amount of the previous month.
At first glance, Tara seems much smarter, doesn't she? In month 1, she gets 100 coins, while Mira only gets 10. By month 5, Tara earns 500 coins, while Mira has grown to 160, still less. But look closely at month 9. Mira's salary has grown exponentially to 2,560 coins, completely overtaking Tara's steady 900 coins.
Mira's clever salary structure is emphatically not an arithmetic progression. It's what we call a geometric progression. This is because she isn't adding a common difference. Instead, she is multiplying by a constant ratio. In her case, the ratio of any term to its preceding term is exactly 2.
We can clearly see that a constant multiplier greater than 1 makes a geometric progression increase significantly faster than an arithmetic progression. But I want to leave you with this final, stimulating thought to ponder for our next class. How exactly would the progression change if Mira's multiplying ratio was a fraction smaller than 1? What would happen to her salary then? Think about it, and we'll discuss it next time. Thank you for joining today's explainer.